like I said before, the two types of series that we're going to be able to compute explicitly are geometric series and telescoping series. It does turn out that we can compute some combinations of the two by using some rules that allow us to split up sums into pieces. And so this rule looks a little abstract when it's written out in terms of variables, but it's sort of obvious when you use it in practice. And so it just says if you have the sum or the difference of two sequences and you're summing it overall, then you can split it up into two separate sums. And also you can pull any constants outside of the sum. And you're allowed to do that as long as both of the sums on the right-hand side of the equation exist and converge. If they don't converge, then you're not allowed to use this rule. And so we'll see a couple examples, one where you can use the rule and one where you can't. And so our first example here looks a little complicated. It's the 1 plus 3 to the n over 5 to the n plus arctan n plus arctan of n minus 1. And so some things to observe with this, first of all, are that this difference right here looks sort of telescopy. And so I might be able to handle that with a telescoping series. And then this right here looks a little messy, but it looks like there are pieces that are raised to powers. And so it looks like it might be a couple geometric series combined. And so we can end up breaking this up into the sum from n equals 1 to infinity of 1 over 5 to the n, plus the sum from n equals 1 to infinity of 3 over 5 to the n, and then plus the sum from n equals 1 to infinity of arctan of n minus arctan of n minus 1. All right, so now I have to compute each of these series individually. And so the first one here, this one is a geometric series where a, the first term of my series, is 1/5, and r, the multiplicative factor each time, is also 1/5. This series right here, same sort of idea. The first term is 3/5, and r is also 3/5 in this case. And so that means that I can plug in for the geometric series formula for each of them individually, and I'll have that the first one is just equal to 1/5 over 1 minus 1/5, because that's a over 1 minus r. The second one is just going to be 3/5 over 1 minus 3/5. And so those are the values of those two already. Now for the telescoping series part, I'll write in a different color, I need to again write out the nth partial sum to see what's going on. So s sub n, the nth partial sum, that'll be arctan of 1 minus arctan of 0 plus arctan of 2 minus arctan of 1, and then plus a bunch of garbage, and then plus the nth term, which in this case will be arctan of n minus arctan of n minus 1. All right, and then as per usual for a telescoping series, we can see that there's some cancellation between consecutive sets of parentheses. In this case, it's that the first term in each parenthesis pair cancels out with the second term in the next set. And so the arctan 1 cancels out, the arctan 2 cancels out, and in the very last term, it's going to be this arctan of n minus 1 that cancels out with whatever's on the previous line. And so when I clean that up, I see that s sub n is going to give me arctan of n minus arctan of 0. And so here we're going to have to remember some trig, and it turns out that arctan of 0 is just 0 anyway, so I can drop that. And so at this point, in order to figure out the value of this telescoping series, I just need to take the limit as n goes to infinity of arctan of n. And so we've seen this in class before. Arctan of n ends up having a limit of pi over 2. And the reason for that is because tangent has an asymptote at pi over 2. And so at the end of the day, then, if I go back and trace through my steps for this problem, the final answer, which I'll write back in green, should be this 1/5 over 1 minus 1/5 plus 3/5 over 1 minus 3/5, and then plus the pi over 2 from the telescoping part. Okay, now let's look at a situation where you cannot break up the sum into two different pieces. And you'll see that this example is pretty obvious. And so if we have the sum from n equals 1 to infinity of 1 minus 1, then of course I could rewrite this as the sum from n equals 1 to infinity of just 0 because the 1's cancel. And so it should be very clear that the sum is just 0. However, if I sort of naively tried to break this up into two sums, which we'll see you cannot do, then I would get the sum from n equals 1 to infinity of 1 minus the sum from n equals 1 to infinity of 1. And if I compute both of those, then you'd end up getting infinity minus infinity, which is indeterminate. And so the problem is that each one of these sums individually does not converge. And so the breakup into these two pieces is not valid here. And so whenever that happens, that if you break something up and one of the pieces is infinity, that does not mean that the sum diverges overall. It means that you have to break up the sum in a different way.